Okay, yeah. And now we start on the second part of our course. So finally we get to the part that we start talking about quantum algorithms. Okay. And yeah, a bit. So we start this a bit before we do midterm. And so before we talk about quantum algorithm, so quantum algorithm is before introducing our quantum algorithm, we need to talk about quantum oracle. Okay. So we have talked about quantum circuits. So quantum circuits are constructed from quantum gates. Okay, so you have those AND or NOT gate, and those X gate, Z gate, T gate, etc. And you can use your quantum circuit to get a quantum algorithm. But yeah, so you can do that. But sometimes people would like turns out it turns out that a good way to think about quantum algorithm is you think about quantum oracle. Okay, so I guess the idea is really you think about, well, you have all those quantum gates, you can do quantum computing, but then you need to think about what problem that you can actually build a quantum algorithm that's faster than classical algorithm. Okay, and yeah, so one of the principles people think about quantum algorithm is we have this quantum superposition, right? So we say everything quantum, they will stay in quantum superposition, and you can do linear things on that. Okay? And so in particular, the input to your quantum algorithm can be you can think about it in quantum parallel. Okay? And so people try to use this superposition and quantum parallelism principle to build a quantum algorithm. Okay? Superposition. Okay. Okay. Yeah, so with the superposition, you have this quantum parallelism that you kind of do computation in superposition. Okay. But this is something a bit tricky because I guess we will talk about this a bit later. This is a bit tricky, so a lot of popular science people say that you have exponential large Hilbert space. Okay, so say you have exponential large Hilbert space, so you can solve everything in parallel. But that's not actually true. So quantum parallelism is a principle that you think about, but it's quite hard to get it actually working. Okay, okay, so there is an exponential big Hilbert space. And question mark is this exponential speed up, but that's not generally true. Okay. Okay, and there are actually counterexamples that we'll see. But for now, let's stop the negative part. Let's stay on the positive part. Okay. So let's see some example of quantum mechanics. Quantum computing actually give us a speed up. And the idea is we have a quantum parallelism, and we can do things in this quantum parallel or quantum superposition, and we'll do like in input. So how is this formulated? Is now we're going to talk about oracle. Okay, so we think about our algorithm. We'll call a sub-algorithm. So we'll do some. Say we will call there is some. Small part of our circuit that will calculate some just a classical Boolean function. So we've learned in our classical computation, a Boolean function is a function that with just one bit output. So it has an n bit input and it will give one bit output. Okay. And so this oracle idea. Okay, so this oracle idea is something that people generalize from classical oracle. So classical oracle, you can think about there is some black box, or you can think about there is some sub-algorithm that calculates the f of x for you. Okay, so your input, so input maybe it's n bit, so maybe let's write a slash here. So it means it's n bit here, so it's an n bit input and 1 bit output. Okay. So you can have some classical, you can think about this in your circuit. as a particular element that will take an bit input and calculate f of x for you. So you have an input x here, and the output will be f of x. Okay. And now we think about what happens when we turn this UF into a quantum circuit. And when we turn this into a quantum circuit, it means that we can calculate this f in quantum superposition. That means that we can have different x as input. So it's kind of like just when you do in, I don't know, in CNOT, right? So or maybe easier gate, maybe X gate. Okay, so you can think about this like in quantum you can turn a classical gate into quantum gate by just extending it to superposition. So this gate has that if you have some A as input, then this is A plus 1 as output. Okay, and when you turn this into a quantum gate, then you think you can have a superposition of input. So say if you have a plus as input, then so this is 0 plus 1, then you will see that 0 plus 1 has 0 plus 1 as output, etc. Okay, and so similarly, we want this quantum superposition thing to happen for every Boolean function, and the thing we get is this quantum oracle here. Okay. And yeah, so quantum oracle is still compute f of x, okay, but you will do it in this weird way. So you will have input register and output register. So input register will be input as some x. So this x is the input x you want to calculate f of x on, and there is an output register that well, you can start with anything. But if you start with some computational basis y, then we'll output with y plus f of x. And I guess here we should have a bit note here. So this xy here is computational basis there. Okay. So we define this oracle in computational basis, just like we define this for every quantum gate. And when you have a superposition, then you will have of x and y here, then you will have a corresponding superposition of output, just the usual linear combination. Okay, and yeah, let's see a bit more detail about this quantum oracle. So for every Boolean function f of x, we can define this quantum oracle UF that will compute f of x in superposition. Okay. And yeah, so f of x is n bit to 1 bit Boolean function, and this UF is quantum gate on n plus 1 qubit. So you need n qubit to write your input, and 1 qubit to store your output. Okay. And yeah, we just claim that if you know this Boolean function f, then you can always get a quantum gate or a small, like a big quantum gate, or just piece together with a basic quantum gates to get a quantum circuit that calculate this classical function for you. Okay. So this part need a bit of proof, but if you are careful, you need a bit of proof. So basically, you say you use Toffoli to do every classical computation, etc. Okay, but we just state this without proof. So we say that it's possible with some universal quantum gate set, you can construct this UF. And what this UF do is it will look at x and compute the f of x and write it on the y register. Okay. And yeah, but when you write down the y register, it's you don't replace y with f of x. You need to do this O plus f of x. Okay. And yeah. And one big thing here is that so it has this weird definition because we know every quantum gate is unitary and reversible. Okay. And once again, this might not be reversible. Okay. So this x go to f of x might not be reversible because classical gate we don't care so much about reversible usually. But quantum gates, just because of quantum mechanics, they need to be reversible. Okay. So we write it in this way. So this O plus, we cannot just throw away y, otherwise it's not reversible. So we add f of x onto y with this O plus, which means addition mod 2. And later on will be slightly trickier. So now this is a Boolean function. So y is 1 bit and f of x is 1 bit. So this addition module is more well defined, but you can probably guess. And sometime soon we'll generalize this to not a Boolean function. And then we'll have a multiple bit of f of x. And then you still need something like this addition module, but a multiple bit. Okay. But anyway, let's go back to Boolean function. So Boolean function, we can construct some logic construct with some basic gate to get this UF. I guess I should call it subcircuit. So it's a UF circuit that will do this calculation here. And so it takes x, y as input, and they will output x and y all plus f of x when x, y is a computational basis. Yeah. Okay. And it is unitary and reversible. That's important because any quantum gate is unitary, and you compose from unitary gates, you should get a unitary. Yeah. And this thing has also a net, so it's called oracle or a query or a black box. Okay, so all those three names basically borrowed from classical computation. So this UF thing here is also called, so it's classically it's also called oracle or black box or query. Okay. And also query can be used as a verb, so sometimes you will also say query and oracle. So query oracle means you to put some input to this thing and try to get some output. Okay. And a bit of a notation here we use UF for unitary, but a lot of time people also use OF, and I think even we in the later part of our course will also use OF. So all because usually we think it is as an oracle. Okay. And I guess maybe a little explanation on this name. So what is oracle? For English, oracle is I think is an ancient priest. You can pay some money to an oracle, and the oracle will tell you, will give you an oracle. I guess that's overuse of name, but it will give you some speech or something, tell you something about your future. Okay, so yeah, we try to abstract this idea. Oracle is something that you can pay the fixed amount of money, and it will give you some information back. Okay. And here, what's the money we get? We pay money. We paid is we need to put a circuit here. So we pay some computation time, and we compute this f over x back. And so query is just the verb that the people use to basically fancy word for ask. So query means asking, and query oracle means ask a question to the oracle. Okay, and then black box. So why is this called black box? It's a bit of a more abstraction here. So here, from our description, this is not really a black box because we say we know this f and we construct it from basic logic gate. But I guess a big idea here is we try to with this oracle construction, we try to abstract away with this construction of f(x) from logic gate. So we don't really care about how UF is constructed from basic logic gate. We just want to know that there is some quantum gate that will calculate UF in this way for you. So black box means that we don't look inside of how this box is constructed. It's so it's kind of a sealed box, and you will take an input and give us expected output. Okay. So it's just a box that's put here, and you can query it and get the answer. Okay, so that's the idea of quantum oracle. And any questions so far? Because so those oracles will be basis of basically all the quantum algorithm we'll talk about in second part of the course. So be very sure about you know what this means. Okay. Yeah. And let's see some quantum part of the quantum oracle. Yeah. And so quantum part of the quantum oracle is we can compute this in superposition. Yeah. And as we said, so let's think about what if our input is a superposition of something. Okay, so the output register, let's just keep it as a 0. Okay, so you don't start with nothing, so there's a blank space you can write down. And let's say we have a 1-bit function, so this n is 1, and so n is 1 here, x is also 1 bit, and so if it's 0, you will compute f of 0, and if it's 1, you will compute f of 1 here. But what happens if you put 0 plus 1 square root 2 as input? So this is a plus state here. Okay. So if you have a superposition input, then we know 0 state will get this 0 f of 0, and 1 state will get this 1 f of 1. And because this 0 plus 1 is a superposition between 0 and 1, then the output is corresponding output. So you have 0 f of 0, and then you have quantum superposition plus this 1 f of 1 as output state. And this output state might be entangled if f of 0 not equal to f of 1. Okay. So you have superposition as input here, you can get the entangled output here. And here we have the state returned as two computational basis state, like we usually do in our circuit calculation. So input state is 1 over square root 2, 0 tensor 0, and 1 over square root 2, 1 tensor 1. And then we could do the calculation separately. So 0, 0 become 0 f of 0, and 1, 0 become 1 f of 1. Yeah, so this is what happens when you put the superposition as the input. And then you can also check that this thing is reversible or unitary, because well, it's its own inverse. If you do the same thing twice, then back to identity gate. It's quite easy. Okay. And okay, so we get quantum superposition here, but if you usually see it in this way, it doesn't seem very useful. Okay. So you kind of calculate f of 0 and f of 1 together in this state, but you cannot get both f of 0 and f of 1 out of this state. Okay. So stupid thing you can do is, I guess not really stupid, but a naive thing you can do is you can just measure this state in computational basis. Okay? And hopefully you still remember how to do measurement. So when you do measurement, then yeah, you try to measure this in computational basis. Then you see that well, both of these are computational basis state, and but there are different computational basis state because the first one here is 0 and the first one here is 1. So and both of those states is amplitude 1 over square root 2. So with 1 over 2 probability, you will get this state, this computational basis as outcome. So you will get 0 on first 0 on first register and f of 0 on second register. And with 1 over 2 probability, you get this 1 on first register and f of 1 on second register. And so what you really care about is probably the second register, and you see that with 1 over 2 probability you get f of f of 0, and with 1 over 2 probability you know f of 1. So it's basically you just randomly compute 1 of f of 0 and f of 1, and that's not much faster than classical computation. So if you allow randomness in your classical computation, you can also just throw a coin and say coin is 0, I will compute f of 0, coin is 1, will compute f of 1. Okay, so there is not really quantum speed up if you just do this. Okay. And yeah, we will see more detailed algorithm soon about what we can do with what more we can do with this. Okay. And I guess maybe the flow is a little weird. Okay. Let's skip this slide. Okay, and let's go to the algorithm that actually do faster on this. That's the Dirichlet's algorithm. Okay, and we said that we cannot get f of 0 and f of 1 together here. And in fact, you can prove that with just one call to this quantum oracle, and you cannot compute both f of 0 and f of 1. But there is something that classical oracle cannot do, but you can do with quantum oracle is you can compute this XOR between f of 0 and f of 1 with just quantum oracle code. Okay, so if you have some 1-bit Boolean function with from 0 to 1 to 0 to 1, and then with one oracle code, so if you just play one of the black box here inside your circuit, then you can compute. Oh, sorry. Yep. Oh, okay, we're back. Okay, so you just need to play one box here, then you can compute f of 0 plus f of 1. And this is it's quite easy to show that this is not possible with classical oracle. So if you don't query in superposition, then you want to compute this thing with, I guess, 100% probability, you always need to, you need to know f of 0 and f of 1. Okay. But quantumly, you can compute this without knowing either of them, and with only one oracle code. And yeah, here is the quantum circuit that do this. Okay, and the quantum circuit do this is this way. So you start. So there is an oracle here. Is only one of them, and then you do other thing. Okay. So there is the X register. You basically start with the plus state. So you start with a 0, and you transform it to with a hidden market. And you basically have a minus state here. So you start with 0, you go through X and hidden mark here. So this is the plus state, and this is a minus state. And we say then if you then you have some output. So you have a really superposition state as your input. Then on the output you do hidden mark on your input register also. Then you do measurement. Okay. And yeah, here you see this is a really quantum thing you do here, because if you just think this is input register, output register, then why are you measuring the input register? Input register should just be your input. But as we will see in calculation, because all the quantum superposition and the interference, then you can actually get your output on your input register here. Okay. So it's something very interesting. And the actual trick here is the big trick here that will use a lot of time in this second part of the course is where we put this weird minus state on the output register. Okay, and yeah, let's see how this thing actually calculate our Dirichlet's algorithm or Dirichlet's problem. So how this calculate f of 0 plus f of 1. Okay. And input, so let's first calculate the input psi 1 here. Okay. Okay. And psi 1, as we said, this is this is hidden mark on 0, and all times hidden mark on 1 because x on 0 is 1, and this is plus and minus state. Okay. And okay, so this is a plus tensor minus state, and because we know what we are going to do next, we want to write it in this not very symmetric form. So write it in this 0 tensor minus plus 1 tensor minus state. Okay, so we're just writing the plus as the 0 plus 1 here, because we know this will give us easier calculation later on. Okay, and okay, then we do the most important trick, this phase key back trick. So we see what happens when we have some computational basis x here as input, but minus state on the output register when we do this quantum oracle or UF. Okay, so this thing is important. I guess I can give a star here. So this is important. Okay, so UF x all times minus. What happens is, well, we can just now let's try to go through this with basic calculation. So okay. So minus state once again is 0 minus 1. Yeah. Okay. So so there is the excuse me. Okay, I guess I should. Okay. So there is a 0 minus 1, and then you will then we know that so y is either 0 or 1, and then we know we will add f of x on the y register. Okay. So 0 register becomes 0 or plus f of x, and not really real register. So the real component becomes 0 or plus f of x, and one component becomes 1 or plus f of x. Okay, it's the same. And minus, it was 0 minus 1, so we have a minus here. Okay, so second register becomes this thing, and we kind of skip ahead a bit of steps. So because we know the first register is the same thing, so then we combine the second register back to this product state. Okay. Okay. So any questions so far? So we have minus is 0 minus 1, and when you apply UF, then you add this f of x onto this 0 and 1. Okay. And now we do case by case analysis of this state. So what is 0 plus f of x and 0 plus and 1 plus f of x. And f of x is a Boolean function. It has 1 bit, so there are really only 2 cases. So either f of x equals 0 or f of x equals 1. And f of x equals 0, obviously nothing happened. So this is still minus state, so you still have x all times minus here. And f of x equal to 1 is the interesting thing happen. So f of x equal to 1, then 0 plus 1 become 1, and 1 plus 1 becomes 0. So you still have 0 minus 1 here. Okay. But the difference is you get a minus sign. So instead of 0 minus 1, you get 1 minus 0 when f of x equal to 1. Okay. And you get a minus sign. Okay. And now, yeah, so now this is the critical part. So minus sign, you kind of feel minus sign is a global phase, but it's not really global phase because this minus sign is different, is not present when f of x equals 0. So this is actually a relative phase between f of x equals 0 and f of x equal to 1. Okay. And yeah, so let's express this as minus 1 to the f of x, because yeah, this is just minus 1 to the f of x, and so it's 1 when f of x equals 0, and minus 1 when f of x equal to 1, and then the other thing, the x all times minus. Okay. And so this trick is called phase kickback, because it can kick the phase onto, it can kick the f of x value from the information about f of x up to this phase. Okay. So and actually do kind of two things. So it become a phase. So f of x become something on this minus 1 phase, and written in this way is a phase on the minus register. But then we use other thing is that when we have the tensor product, and you multiplying a scalar on tensor product, it's same either as you have the phase on the minus register or the phase on the x register. Okay. So this is the kickback part. So the calculation result was on the second register, but because we write it as a phase now, so this phase can really be appended on any register. And in particular, we can think this phase is on the first register also. Okay, so this is a phase kickback. Any question? Yeah, and this thing is something we'll do a lot in the second part of the course, where we have this quantum oracle, which is just a classical oracle in superposition, and we turn it into something really quantum. So this phase expression is really something that you can never get from classical oracle. Yeah, this phase version, later on we will talk about this as a phase version of oracle. So where instead of just have your f of x add on to the second register, you have f of x just being an exponent on some phase here. Okay, so phase version of oracle, and is converting the standard version of oracle to phase version of oracle is called phase kickback. And in this simple example, we see that we can do this by just using the minus 1 as input to your output register. Okay. Okay, and once we get the phase kickback, then we can calculate the output of oracle quite easily. Okay. So we know our input. Okay, so go back a little bit. Remember our input is this 0 all tens minus plus 1 tensor minus. Okay, and we know what the UF do on x tensor minus on computational basis tensor minus, and you will get this phase. Okay, so we have a UF on 0 tensor minus and 1 tensor minus, and as we said, now this oracle will just write the result as a phase. So this is 1 over square root 2, and once again in superposition. And so the first component will get minus 1 to the f of 0 because x is 0. And the second component will get a phase of minus 1 to the f of 1. Okay? It's just corresponding to this minus 1 to the f of x. And x equals 0 here, and x equals 1 here. Okay, 0 here, 1 here. Okay, and we get this side too. And we're almost done, so let's do a bit of cleanup here. Okay, and now we take out something that's really a global phase. Okay, so we take our minus 1 to the f of 0 factor. Okay, we take our minus 1 to the f of 0 factor. So on the first register, on the first component, this is just a 0 tensor minus now, and on the second component, we need to compensate for this minus 1 to the f of 0. So this minus 1 to the f of 1 become minus 1 to the f of 1 minus f of 0 here. Yeah, so this is just some mathematics taking our global phase. Yeah. And then after we do this, we see that our state is actually something simple. Okay, so the second register is always minus state. Okay, and now the first register is this 0 plus minus 1 to the f of 1 minus f of 1, 1. Okay, and yeah, that's maybe write down the first register in detail here. First register, so we can write down the first register is also 1 over square root 2, 1 over square root 2, and 0 plus minus 1 to the f of 1 minus f of 0, and 1. Okay. And so this thing is, so this is a very complicated expression here, but remember this thing is just either minus 1 or 1. Okay. So this is a very complicated expression, it's just either minus 1 or 1. So you are either having 0 plus 1 or 0 minus 1 here. Okay, and when it's 0 plus 1 is plus, and when it's 0 minus 1 you have minus. Okay. And so when do you have 0 plus 1? It's when basically 0, f of 0 equal to f of 1. Okay. When f of 0 equal to f of 1, you have minus 1 to a 0, so this is a plus state here. And when f of 0 don't equal to f of 1, then you have minus 1 to either 1 power or minus 1 power, but it's all minus 1. Okay, so when f of 0 not equal to f of 1, you get a minus here. Okay, so the state you get is this global phase minus 1 to f of 0, and depend on whether f1 equal to f of 0, have plus or minus here, then tensor 0. And yeah, then okay, so we're almost done, so you can almost see the answer here. Then lastly, we just do head map and measurement. So what the head map do here is you will just turn this plus and minus into 0 and 1. We know head map is transformation between plus minus and 0, 1. So you get 0 and 1 here, then you measure the first register. So we see that your measurement result will be 0 if f of 0 equal to f of 1, and the measurement result will be 1 if f of 0 don't equal to f of 1. And this is exactly what we want, even though we're saying this, yeah, I guess we can start with this, but anyway. So this f of 0 equal to f of 1 just means that f of 0 or plus f of 1 equal to 0, and f of 0 don't equal to f of 1 just means f of 0 or plus f of 1 will equal to 1. Okay. This is just a simple bitwise addition. Okay, and yeah, so that's our Dirichlet's algorithm. We see that with this phase kickback, we can calculate f of 0 or plus f of 1 with just one oracle, quantum oracle code. And also, I guess interesting part is that we know neither of 0 or of 1. Okay. So we didn't explicitly calculate f of 0 or f0 or f1. We just do everything in this quantum superposition, and in the end we get this all plus result. So we can do a bit of information counting. So we see that although this is not quite precise, but anyway, we see that with this one quantum oracle code, we get 1 bit information about this function f. Okay, and yeah, and that's I guess a question so far about Dirichlet's algorithm. If not, then I guess let's go back a little bit to explain this more idea about quantum oracle. Okay. So one thing very funny we do on this Dirichlet's algorithm is well, this algorithm compute well some output f0 or path f1, but then you kind of think about what's the input to this problem. Okay. So output is this f0 or path f1. And the input is really this f here. So because usually, so when we talk about circuit model, we say that well, the left-hand side of a circuit is input, but here the left-hand side of a circuit is really not your input. The left-hand side of your circuit is 0, 0. No matter what your output is, the input is just 0, 0. Okay, and so input here is really this f. Function f here. Okay, and yeah, so this is something funny that happen in this oracle algorithm is this quantum oracle. We can also think them as input to your quantum algorithm. Okay, so yeah, so you will think your this function f of x is input to your question. Okay. And so something very confusing here is that this is a function. So there are really two inputs in this description, and hopefully don't get too confusing. There is the input to your f of x, and also f of x itself is the input to this Dirichlet's algorithm. Okay, and anyway, so let's talk about the input to our this outer algorithm. Is this function f, and we can just express this. We can just think of this as well also a string input, and the input is the truth table of f of x. Okay. And yeah, okay. So say our f of x is an n-bit function, then there are 2 to n possible input to f of x, and corresponding also to different bits of the output. Yeah. And I guess here we have an example of n equals 3, but we should, so in Dirichlet's algorithm, then we should really start with n equal to 1 example. Okay. And there are, the input is basically a 2-bit string. Okay. So there is f0 and f1. Okay. So we can think about the input to Dirichlet's algorithm is this 2-bit string f0 and f1, and yeah, so a classic algorithm to calculate this thing, you can read the input totally, you can query f0, query f1, and then you add together the output, and you get the correct result. Okay. But in quantum algorithm, we see that we can do this with one query. We can query f0 and f1 in superposition, and calculate this addition between them in just one quantum oracle code. Okay. Yeah. So this is kind of like another way to think about query algorithm is you have this truth table as the input. And yeah, and you think about algorithm is trying to ask you a truth table about different slot of this truth table, and the algorithm will try to compute some function on this truth table with as little quotient as possible. So here they ask this quantum quotient, what's this superposition query. So I guess really as one quantum quotient on this f0 f1 oracle, and the quantum algorithm is able to compute f0 or plus f1 with just one quantum quotient as compared to classical algorithm need to ask both f0 and f1 to compute the f0 or plus f1. Okay, and yeah, so this is a bit of a confusing description because there are two inputs, and also a bit of a notation usually used. So the number of bits that's the input to f of x is usually called small n, and then we usually call big N as 2 to n. That's the number of bits in this truth table of small f. Okay. So say n equals 3, then here we have big N equal to 8, and that means that when you try to write down the truth table of small f, then you need to write down 8-bit string. And in our Dirichlet's algorithm example, small n equal to 1, you have small n equal to 1 and big N equal to 2. And as we see that because the truth table of a small f is actually a 2-bit string. Yeah. And we have time to continue, but I think we already talked about a lot of the concept here. So maybe let's stop here. Okay. And yeah, a bit overview of next time. Then this is a very simple example. This is just algorithm showing that there is some problem that you need to do with two classical query, but can do with one quantum query. And then we'll start talking about algorithms that give even bigger separation. So there is a Dirichlet's algorithm that says that you need to do this with 2 to n. I think it's 2 to n classical query, n classical query, and with one quantum query, and there is even more complicated question. There is this bursting inverse running algorithm, and there is this segments algorithm. Okay, so yeah, a lot of quantum algorithm to see, and but all of them follow the similar structure. I think. Yeah, all the algorithms we talk about here basically are solved by this phase kickback tree. So we'll keep doing this and have the output register, this f of x information, phase kickback to the input register, and yeah, do some Hadamard transformation here or other transformation here and do measurement. Okay. And yeah, so see you on Thursday. Let's see, we'll do midterm explanation and handout on Thursday, but we'll see whether we have extra time and decide whether we want to talk a bit more on quantum algorithm. Okay, yeah. So anyway, yeah. So see you on Thursday. There will be midterm handout and maybe even a bit more quantum algorithm.